Greetings, Chem 1 students. This is Mr. Braun, and today we are going to talk about balancing redox equations. We're going to learn a couple of tricks to help us balance a redox equation. Sometimes these equations are very, very complex. They're tough to balance, so any clues that I could get to help me balance them would be awesome. So today we're going to discuss that. Our learning target for today's lesson is to identify a chemical reaction as an oxidation reduction reaction. Okay, so we're going to make this redox reaction, we're going to identify it, and the success criteria to help us do that is we're going to identify atoms that are oxidized or reduced through electron transfer. We are going to assign oxidation numbers to atoms in compounds and in ions. We are going to identify redox reactions by analyzing the changes in these oxidation numbers. And finally, we are going to balance equations for oxidation reduction reactions through the oxidation number change method. Well, folks, those four things we are going to need to be able to do to balance these chemical or these redox reactions. So let's just jump right in. Simple redox equations can be balanced by inspection or by trial and error. The way that we've been balancing equations is we've just been looking at numbers, popping them in. If it didn't work, we'd have to erase them and go back and do it again. However, as I said before, these redox reactions are somewhat more complex. They could have, multiple products, multiple reactants, so it's not real easy to balance. Thus, we use two systematic methods to solve these complex reactions. Those two methods are the oxidation number change method. That is the one that we are going to do today, the one that I am going to teach you, because I think that that one is the easier of the two. And the second one is the half reaction method. These methods are based on the fact that the total number of electrons gained must equal the total number of electrons lost. So the electrons gained during reduction, remember, gain electrons reduction, GR, lose electrons oxidation, LEO, GR. Remember that the amount of electrons that are lost in oxidation must equal the number of electrons that are gained in reduction. That's the key part of these oxidation number change methods. So I'm going to take you through 5 different steps here, folks. And of these 5 steps, we're going to walk through the process of how to balance an oxidation reduction reaction. So, using the oxidation number change method, the first step we need to do is we need to assign oxidation numbers to all the atoms in the equation. Step number 2 is to identify which atoms are oxidized and which atoms are reduced. The third step in the process is to use a line to connect the atoms that undergo oxidation and a line to connect the atoms that undergo reduction. And you need to write the oxidation number change at the midpoint of each line. Now, folks, you might not understand what I'm talking about right at this point with this step, but I am going to show you. We are going to model 2 of these coming up here, and I'm going to walk you through the steps. So don't panic just yet. We're just getting all 5 of the steps down right now. The 4th step is to make the total increase in reduction number equal to the total decrease in oxidation number by using appropriate coefficients. Okay? Probably the thing that you're going to do with this is to find, in this math term, find the least common multiple of these numbers. And finally, the 5th step is we are going to use these coefficients that we got in step 4 to give us ideas of how to balance the redox reaction. So we use those coefficients that we have up here in 4, these coefficients right here. We're going to use those to give us hints to balance our chemical equation. So what we're going to do is we're going to jump right in to this first example here. Now, my step number 1 is to assign oxidation numbers to all the atoms in the equation. Now, we've already talked about oxidation numbers, so what I'm going to do is I'm just going to come up here and write down what I know. I know that this is not a peroxide, so that's going to be -2. The net charge of these has to be equal to 0, so this is going to be +3. So my total from iron is going to be +6. My total from oxygen is going to be -6. Once again, I look at this carbon monoxide here. I see this oxygen. It is not a peroxide, so that's got to be a -2 for oxygen. There is a +2 for the carbon. The iron right here is by itself, so it is taking a 0 oxidation number. And then I finally finish off with my carbon dioxide. Once again, this is not a peroxide, so that's going to be -2. So that has a total of -4 charge, so this carbon has to be +4. So I have put my oxidation numbers with each one of the atoms involved, and I need to identify what is being oxidized and what is being reduced. Well, as I'm looking here, I see that iron on the product side of my reaction, is 0. And iron on the reactant side is +3. Okay? So iron is one of my changes. The other change that I see, my oxygens are all -2, so that's got to leave my carbon right here. My carbon in the reactant side is a +2. My carbon in the product side is a +4. So I have identified which atoms are changing, okay? So let's look at this. The iron goes from a +3 to 0, okay? So in order to go +3 to 0, I have to be gaining electrons, okay? I have to be gaining electrons. Gain electrons reduction, grr. So iron here is being reduced. All right, let's look at the carbon. Carbon has a +2, and it goes to +4. So I am losing 2 electrons, okay? I'm getting more positive, so I'm losing electrons. Lose electrons, oxidation. So in this particular instance, my carbon here is being oxidized. Now, step 3 is that confusing one where we need to use a line to connect the atoms that are undergoing oxidation and those that are undergoing reduction. So I'm just simply going to connect my iron, and then I am going to connect my carbon. And after I connect them, I'm going to write down which is doing what. So carbon was losing electrons. So carbon was being oxidized. That means that my iron was gaining electrons. So my iron is undergoing reduction. Now, how much? How many electrons did my carbon lose? Well, it lost 2 electrons. How many electrons did my iron gain? Well, it gained 3 electrons. Okay, so I can see the changes. The carbon lost 2 electrons. The iron gained 2 electrons. Now, here is the tricky part. Okay, step 4 says to make the total increase in reduction equal the total decrease in oxidation. So what I'm doing here is, since I have reduction gaining 3, I have oxidation losing 2. I'm finding my least common multiple between 3 and 2. And in this instance, that makes 6. So when I look at my reduction here, I'd need to multiply that by 2 to get a plus 6. My oxidation, I'd need to multiply that by 3 to get a minus 6. So now I've found my least common multiple for these two, and that's where I'm gonna get my hint. My hint is gonna be 2 right here for iron. My hint is gonna be 3 right here for the carbon. So as I come back up to my equation, okay, I'm going to balance this guy based on my hints. Well, my hint says for iron, I need to have 2. Well, for this iron right here, I've already got 2. This iron here, I'm going to put a coefficient out in front, 2, because my hint tells me I need 2. What does my hint tell me for my carbon? Well, my hint carbon right here tells me 3. So I'm going to put 3 out in front of that carbon, 3 out in front of that carbon. So now when I go through and I double check, okay, I look at step 5, says to check to be sure that the equation is balanced. Well, I look at iron, okay, I look at iron. On this side of my reaction, I have 2, and I have 2 irons over here. I look at carbon. I have 3 carbons on this side of my reaction. I have 3 carbons on this side of my reaction. Now, all I have to do is look at my oxygens. Oxygens 3 times 2 right here is 6 oxygens over here. If I look on this side, I have right here 3 oxygens, and I have right here 3 oxygens, so I have 6 oxygens there. So I have now balanced this redox equation, this redox reaction. Now I move on to my final one. This is a little bit more complex because I have 3 reactants. I have 3 products, but nonetheless, I'm going to follow my rules. I'm going to follow the steps. And my first step told me that I need to assign oxidation numbers to everything. So as I go through getting oxidation numbers, once again, this is not a peroxide, so that is going to be -2. Potassium is an alkali metal, so potassium is going to be +1. So I have to find out what chromium is, okay? This oxygen right here gives me 14 negatives. This potassium right here gives me 2 positives. So that tells me the number in there is going to be +12. Well, if I have 2 chromiums, each chromium's got to be +6. So now I've done that particular compound. Water right here, oxygen's not a peroxide, -2. Hydrogen's going to be a +1. Sulfur here is by itself. I'm going to make that a 0. Now once again here, I have hydroxide. My oxygen's going to be a -2. My hydrogen is going to be a +1. My potassium is going to be +1. So that is all equal to 0. I come over here, once again, oxygen's not a peroxide, -2. So that means -6. So this has got to be a +3 for that particular chromium. And finally, my oxygen here is -2. It's not a peroxide, so my sulfur has to be +4. So as I'm looking there at my step 2. I need to identify what is oxidized and identify what is reduced. So I'm going to do this and kind of combine for this one, step 2 and step 3. I'm looking and I can see that potassium is 1 on both sides. I have a change in chromium right here. My chromium goes from a +6 to a +3. So +6 to +3 means that it is gaining 3 electrons. So gain electrons reduction, GER, gain electrons reduction. I come back and say, okay, what is the other thing being changed? And usually when I see something like this with a 0, I have a good idea that that's going to be changed. So my sulfur there is going from 0 to +4. So it is losing 4 electrons. Okay, put my little minus there. It's losing 4 electrons. Lose electrons, oxidation. Our old Leo here. Our old Leo. So I have determined what was oxidized. I've determined what was reduced. I've seen the number changes. Okay. Now what I need to do is I need to make the total increase in reduction number equal to the total increase in the oxidation number. So I'm dealing with a 3 and a 4, and I know my least common multiple of 3 and 4 is going to be 12. So I'm going to have this to be 4 to give me a +12. I'm going to have this to be 3 to give me a -12. So now my electrons gained and my electrons lost are the same, and I have my hint. And my hint here tells me that chromium should be 4. Well, right here I have 2 chromium, so I'm going to put a 2 there. Over here I have 2 chromium, so I'm going to put a 2 there. So I'm going to have 2 chromiums right there. My hint for my sulfur tells me that I need 3. So since I only have 1 there, I'm going to put a 3 here. I'm going to put a 3 here. So now what I'm going to do is I'm going to use these 2 to balance up the rest of the stuff that I have. So where am I going to start with? I'm going to start with that potassium because I can see over on this side I have 4 potassium. So I'm going to put a 4 right in front of there so that I have 4 potassiums. Now, I've only got one other place where I can put a coefficient right there in front of my water. So I'm going to look at my oxygens, okay? I'm going to look at my oxygens and my hydrogens, and hopefully they balance out. Well, it's going to make it real easy because I can see on my product side of the reaction that I have 4 hydrogens, okay? I can see right here that I have 4 hydrogens. So hopefully if I put a 4 right here, that will balance out all of my oxygens. So let's look on my reactant side. Oxygen, 7 times 2 is 14. 14 plus 4 is 18 oxygens on that side. I come back over to here. I have 4 oxygens there. I have 3 and 2 is 6. And then I have 4 oxygens. 3 and 2 is 6. 3 and 2 is 6. So 6 and 6 is 12. 13, 14, 15, 16. Okay? Wait a second here. What is not making sense? Okay? 14, 15, 16, 17, 18. Okay? 3, 2 is 6. 3 and 2 is 6 is 12. 16. I am off. Oh, I found it. I found it. Okay? Right here. Right here, ladies and gentlemen. I have made a mistake with that one. Because what did I do? I have 4 hydrogens right here. Okay? I have 4 hydrogens right here. And I have 2 here, so this should be a 2 to get that to 4. Okay? That should be a 2 to get that to 4. My hydrogens were not on balance there. So let's go back now again. Woo! That was a toughie. Let's go back now again and look at my oxygens. So I have 14, okay, plus 2 to give me 16. Boy, I think this is going to work out a little bit better because now I have 4 oxygens there. I have 6 oxygens in my second compound there, and I have 6 oxygens in my third. 6 and 6 is 12. 13, 14, 15, 16. So now indeed my oxygens are balanced. So see, I've been doing this, ladies and gentlemen, for many, many years, and I still make some mistakes on these. So it's good that I have everything written out, so when that thing did not balance, I could go back and look and say, okay, what is the deal? Why was that not balancing? And we got the whole thing figured out. So now I have a balanced redox equation in front of me. So, ladies and gentlemen, this has been Mr. Braun. This has been our discussion of balancing redox reactions. Everyone, have a wonderful day.